All right, last example. I'm going to have two more vectors. And we're going to project them, but this time we're going to do a vector projection. Now, the next obvious question from you guys is, Miss, how do we know if we're doing a vector projection or a scalar projection? Is that the next obvious answer? The question will say, vector projection, scalar projection. And if you guys have this conceptual understanding of what's going on, you will absolutely be fine. So this one is this vector and this one is this vector. Have I got the right way around? Yes. So can you find me? We'll work through together projection of A onto B. And then for those who want to go ahead, we are going to do the projection of B onto A as well. So, for those of you who want to do this in one step, you can. It gets a bit messy. I'm going to show you how to do it in one step, and then I'm going to try and convince you that it's better to do the components.
The formula there, is that projection A onto B?
Yes, one. Yes.
Okay.
Yep, that one's A onto B. Sorry?
It's not a formula sheet.
The projection one?
Yeah.
No. But dot product is.
Yeah.
Okay, so what do we need to do? I'm going to use this version here. So I have vector A dot unit vector B. What's unit vector B? Unit vector B, B over magnitude of B, so it's going to be B over magnitude of B. Do you see what I mean about getting messy? That's our first brackets. That's this bit. A dot unit vector B times, or dot, unit vector B again. Now, if I was doing this working and when I've been working through them, it's much, much easier if you go and work out unit vector B first. Do you agree? So let's work through this one again. Unit vector B is, what's this? 4 plus 9, which is? So square root of 13. So I'm going to take this out the front. And because, remember, right back to the beginning of today's lesson, you can bring that out the front of a dot product. I can now just do this. And this I'm kind of comfortable with, except for my brackets. Then I have times another 1 on root 13 times minus 2i plus 3j, which is just this. I can bring these two out the front. These two, I get 2 times minus 2 plus minus 5 times 3, and I still have this vector out the back. What's this value? Minus 19. Can I go any further? What'd you say?
I said I'd like to say no.
I'd like to say no too, so I'm really glad you'd like to say no. I have a scalar multiple of a vector. That means I have a magnitude change, in this case a direction change, in the direction of B, or in the opposite direction of B for this one. Are we okay with that? So you can do it in one step, but if you're not great at your surds, if you don't really like to have everything all jumbled in together, because this is complex, then take it offline. So for me, if I was starting with projection of B onto A, what's the first thing that I would need? Which unit vector? I need unit vector A. And I can do that very quickly by doing A over, I'm trying not to give you the answers, A. Then you've got this bit and this bit all sorted. So I'm going to give you a second and then we're going to do up the answer. So unit, I want the projection of B onto A, the vector projection of B onto A. This is the unit vector A, which we use twice. So now I just need to do this bit here, but you've already got an expression for that and that. So have a go. I'm running right down to the bottom of the board. Anyone got me an answer? I can already see it's going to be something over 29 in the direction of A. So it's going to have vector A hidden in it. It's got to have direction of A hidden in it. So the only thing you're really finding is that numerator. Minus 19. No.
2i minus 30.
Sorry for running into my diagram. But my 29 is here twice because remember here and here. So that's why it's not root 29. This is the scalar dot product of A, B in the direction of A. So not only can you do this, but in the exam you can go, good, I've got a scalar multiple in the direction of A. Nailed it. All right, last thing before I let you guys go. I know it's been a long theory lesson because there's a lot of, do you notice how all of the notation suddenly went, and you all went, I thought I was good. What is the other component? So the perpendicular to the proj A onto B. What's our perpendicular component going to be? It's going to be my A vector minus this bit here is this bit here. So that minus becomes a plus. Working that through, I've got 2i's plus minus 38 over 13. Do we need to take another step? I'm happy to take another step. 2i's minus 5j's minus 38 13ths i's plus, someone help me. 60 minus 357, 13 j's. Don't trust my arithmetic. How many i's do I have? 2 and? Yeah, that. 26 minus 38. What's 26 minus 38? Minus 12. 13th i's. Someone help me with my j's. What's minus 5 plus 57 over 13? Minus? 8? Now, we're in the opposite direction. We're perpendicular to B. I want you, my last little bit, let's have a quick look. 3 and 2. 3 and 2 the opposite way round. We've got our negative there, so we would end up with a 0 dot product because they're perpendicular. That one's in the direction of B. Sorry, that one's in the direction of B, and this one is perpendicular to it. Lots and lots of notation there. But really try to think, all I'm doing is popping it down, seeing what its shadow was, and then sending it in a certain direction. Are there any questions?
What are the practical applications of projection?
This would be how we would resolve, say, let's say I was jumping off a ski slope down onto a sloping mountain. I could resolve my components of my jump into along the mountain and perpendicular to the mountain.
Oh, okay, so when you can't do it, like...
Well, when it's easier to do it on a slope. How did I get 19 over 13? This bit? This bit is this. Because remember, it's just A minus this projection, and so it's then minus minus. Good question. Other questions? That's a lot of information, guys. It's why projections are left right to the end. All right. We don't have long left, so I'm going to set you very few questions. Next lesson, we'll go back into dot product. No. Next lesson, we'll go back into dot product. But remember, this is the last tool that I'm putting into your toolbox. So just try and get your heads around it, and then we'll start applying next week. So I want you to do exercise. All right, have a go.
Spicy.
Actually,
I hate you.
now, just a quick discussion. I think it's useful to separate a scalar projection from a vector projection, so I've done that. Cambridge doesn't make them separate things. So in Cambridge, they won't ask you for a scalar or a vector, they mean the vector. But I thought it was useful to do our scalar and then shove it into the right direction. Because if you can do your scalar, you can just multiply it by the unit vector and we're good to go.